Hello dear classmates, welcome back to the Sequential ATPG chapter. In this video, we are going to introduce a new time frame expansion method, the backward time frame processing. We will talk about two algorithms, EBT and the back algorithm. In the previous extended D algorithm, we use both forward and the backward time frame processing. That means sometimes we use forward propagation like the green path. We propagate the Fourier effect to a primary output for observation. And sometimes we do backward justification to the primary input so that we can justify the required values. But the problem is sometimes the justification can fail. In case of justification failure, we need to backtrack and change our propagation path or justification path. For example, if we have a failure here, then maybe we will try to expand time frame to the right for one more time frame. And we try this new propagation path. In case we encounter another justification failure, then we would try some other path. Finally, we propagate the Fourier effect to the primary output and the test is generated. Totally, we use 5 time frames to generate this test. This seems to be okay, but for large circuit, it's very difficult for us to manage the memory because it's hard to predict how many time frames we are going to need. So this is a big problem, especially for large circuits. In 1978, the EBT algorithm was proposed, which only used backward time frame processing. No forward time frame processing is needed. The algorithm is pretty simple. In the first step, we select a path from the fourth side to the PO. For example, this green path is supposed to be our chosen propagation path. And then, in the second step, we sensitize the path backward from the PO. And we justify the required values in a backward direction. No forward propagation is needed. For example, we do this backward justification. In case we have not finished all the justification, then we can move time frame to the left. Now we create a time frame to the left. At the same time, we can remove this time frame so that we can continue to do the justification. So in case there are still unjustified value, we can now move to the left for another time frame and we remove one time frame. Finally, we can now justify all the values from the primary input. So we generate our test. As you can see, all the time we remain 2 time frames in our memory. So this is very good for memory management. Now let's see an example. Given this circuit, please generate a test for stochastic 04 using the EBT algorithm. We only keep 2 copies of the circuit in our memory. On the right is the current time frame, on the left is the past time frame. So we duplicate the circuit into 2 copies, and we select this propagation path, and we remove the flip-flop and connect these 2 copies by a wire. Now let's try to generate a test using the EBT algorithm. From the primary output and this given path, we will need a 1 here, so we backtrace to input A. And now to sensitize this NOR gate, we will need a 0, which has already been achieved by A equal to 1. Now we want to justify the 1 value from the past time frame. So along this chosen path, if we want to sensitize this path, we backtrace to B, which is assigned to 1. We also need a 0 from the left time frame. Now we can remove the current time frame and move the past time frame to the current time frame, and we add 1 more time frame to the left. Now we can continue our backtrace. To justify a 0 here, we can backtrace to A and B, which are both equal to 0. Now we generate a test where AB is equal to 0, 0, 1x, and x1. This test is successfully generated. Now it's time for you to work on this quiz. Given this circuit, please redraw this circuit into 2 time frame models. Now please pause the video and draw the 2 time frames. Okay, are you done? We simply remove these 2 flip-flops and connect them by wires. Have you got it correctly? Now, given these 2 copies of circuits, please use EBT to generate a test for this stuck at 04. Now please pause the video and work on this quiz. Okay, have you done yet? Given this sensitization path, we can now sensitize this NOR gate by assigning H to 0, so A is backtraced to 0. Now we want to justify a 1 along this path, and now we want to justify a 0 along this path. So now we can remove this current time frame, and we have 1 more copy of the past time frame. Let's continue to backtrace a 0. Now we backtrace a 1 to the left. If you watch this value carefully, you would observe that this is actually the same as our previous justification. So now we are trapped in a cycle. If we continue to backtrace this 1, we will repeat the state again and again. So this is what we call a state repetition. In this case, actually the justification fails due to the state repetition. So now we know this was a wrong decision, so we need to backtrack to another path. Now let me give you a short summary. When we use the mixed forward and backward time frame expansion method, we can reuse the existing D algorithm to handle the sequential ATPG problem. But there are too many time frames. To avoid this problem, we introduce backward time frame processing only method. This method has the advantage that it has fixed time frame and the state repetition can be recognized. But the problem is that there are too many paths. How can we choose the path correctly? So we need some help from test measure to make smart decision. Now let's introduce the second algorithm, the back algorithm proposed in 1988. Instead of explicitly choosing a path, the back algorithm proposed to select a primary output for fault detection. And the primary output selection is based on a testability measure called drivability. When we choose a primary output, the sensitized path will be automatically created with the drivability measure calculated. So the back algorithm choose primary output instead of path, so that we can avoid the problem of the exponential number of paths. Now let's have a short review about the scope testability. Remember that we have CC0 and CC1, which measure the minimum number of combinational PI assignment and logic levels required to control a 0 or a 1 on node N. The scope testability measure estimates the effort to control signal to 0 or 1. So when the number is smaller, it means it's easier to control the node. For example, if we want to control the AND gate output Y to 0, we can have either 0x or x0. So we take the minimum of CC0x1 and the CC0x2 plus 1, which represent the AND gate itself. On the contrary, if we want to control the AND gate output Y to 1, then we need both 1s on x1 and x2. So we take the summation of these two numbers plus 1, which represent the AND gate itself. We can analyze the scope number for OR gate and inverter in a similar way. And for primary inputs, they're both CC1s and CC0s are 1. Now, this is a proposal from the back algorithm, D01 and the D10. They estimate the effort to propagate a D or D prime from the fault side to node Y. D01 of Y is the drivability of D prime to node Y, and D10Y is the drivability of D to node Y. So drivability is very similar to the scope measure for a specific fault. For example, for this AND gate, if we want to propagate D to the output, we can have three possibilities, either D1 or 1D or DD. So we take the minimum of three numbers here and the plus 1, which means the AND gate itself. So we either control x1 to 1 and x2 to D, or x1 to D and x2 to 1, or both inputs are D. Similarly, if we want to control y to d prime, then we also have three possibilities. So we take the minimum of these three numbers plus 1. The drivability of OR gate and inverter can be analyzed in a similar way. For a flip-flop, we add a certain large constant K to the drivability of the input. This K is a user-defined parameter. Typically, we use a large number to represent the effort to propagate the D through a flip-flop. Now let's see an example. Suppose for this 4-free circuit, we already calculate their scope testability. For this node, it's 5, 9. For the clock, it's 1, 1. So the output of this flip-flop would be 7, which is 5 plus 1 plus 1, and 11. Please note that this number is slightly different from those in the textbook. Now let's see an example with testability calculation. Starting from the scope, suppose we want to calculate the drivability of this fault. Since this is a stuck at 1 fault, if we want to drive this node to D prime, then we just need to control this node to 0. So we take the CC0 of this node. So the drivability D01 of this node will be 4. However, if we want to drive this node to D, it is impossible since this is stuck at 1 fault. So we cannot drive it to 0. So it is infinity. Similarly, for this side input, both the drivability D01 and D10 are infinity. Now we want to propagate this D prime to the output. D01 is 9, which is equal to drivability D01 with the side input assigned to 1. So we take CC1, which is 4. We add them together plus 1, which will represent the AND gate itself. So D01 of this node is 9. And it's impossible to create a 1, 0 here. So D10 is infinity. And then we can further propagate this drivability through this NOR gate. So D01 is infinity since for the input D10 is infinity. And the output D10 is 20, which is 9 plus 10 plus 1. Okay, if we want to propagate this drivability through this flip-flop, we will need to add a large number K. In this example, we use K equal to 100. So D01 is now 109. And the D10 is still infinity. Finally, at the primary output, we have D01 equal to 120, D10 equal to 28. For this output, D01 is infinity and D10 is 32. From these four numbers, we can now pick this primary output as our target, since this one is the smallest, which means that If we propagate the full effect along this green dashed line, it will be the easiest. So the back algorithm would pick this primary output and try to propagate the full effect through this dashed green line. Now it's time for you to work on a quiz. Based on the given scope testability measure, now please calculate the drivability for this socket 04. Assume that the constant K is 100. Now please pause the video and work on this quiz. Okay, and you finish? Now let's see the answer. Starting from this fourth side, D01 is infinity since it's impossible to create a 1 here. And the D10 is equal to CC1, which is number 8. And if we go through this flip-flop, D10 would be 108. And now we propagate this number through this OR gate. So the drivability would be infinity and the 110. Through this inverter and also this AND gate. Finally, through this NOR gate. Now we have 4 numbers. Out of these 4 numbers, this one is the smallest. So that means it's easiest to propagate the full effect to this output. Have you got these numbers correctly? Now in summary, in this video, we introduce the backward timeframe processing only method, which has the following 2 advantages. First, we need only a fixed number of time frames, so the memory management is easy. And the second, we can recognize state repetition to stop our backward justification. It saves us a lot of time. So, in this video, we introduce 2 algorithms in this category. EBT algorithm select one path at a time, and the back algorithm propose to use drivability to help us to make a good decision and select a best PO. Actually, in this table, we can see that there are mixed forward-backward time frame method and the backward time frame method. Actually, there is a third method, the forward time frame only method. In this method, we don't need to justify any value backward. We only perform a forward simulation. But it's very hard to decide how many time frames do we need in advance. If we want to know more details about this kind of algorithm, you can search for papers such as fast test algorithm, which is a Poden-like algorithm. Okay, before we end this video, we have 2 FFT for you. FFT number 1. When we calculate the drivability, do we need to feedback this drivability and iteratively calculate the drivability? Question number 2. For the forward time frame processing technique, can we just fix the number of time frames just like the EBT algorithm? Please think about these 2 interesting FFT. Thank you for your attention.